LeetCode Problem 3, longest substring without repeating characters, isn't just an interview staple. It echoes real-world demands. Think live user tracking or stream processing, where redundant scans waste precious milliseconds. The brute force way looks simple, but it's painfully slow. So how do we dodge billions of wasted cycles and engineer something leaner? Let's go full duck-tective and brute force our way through, checking every possible substring for uniqueness. It's slow, but it builds a solid foundation. First, we set up a variable to track the longest substring we've found. Since we haven't started scanning yet, that begins at 0. We'll scan every starting point in the string using the outer loop, anchoring the beginning of each possible substring. The inner loop stretches the end of that substring. We go one past to include each character up to that point. At each step, we'll check if the current substring holds only unique characters. If so, it's a candidate for longest. If it's unique and longer than what we've seen, we update our max length to reflect this new best. To keep our main logic clean, we'll offload the uniqueness check into a helper function we can reuse. Inside that helper, we fire up a set to track scene characters, perfect for constant time lookups. We scan character by character. If one shows up twice, we bail early. This substring has a duplicate. If the character's new, we toss it into the set and keep scanning. If we reach the end, the substring is all clear. Once every substring's been tested, we return the maximum length we recorded, our final result. This brute force method runs in big O of n cubed. For 50,000 characters, that's trillions of checks, not ideal. Space stays at big O of min of n and m, where m is the character set size, manageable for ASCII. But there's a smarter way. What if we didn't restart every time? What if we slid through the string, trimming duplicates as we go? To do that, we'll use a set to hold the current characters in our sliding window, letting us check for repeats fast. We'll set up 2 pointers, one for the window's start, one for its end, and we'll track the max length as we go. While our right pointer hasn't reached the end, we'll keep sliding, scanning each character exactly once. At each step, we grab the character under the right pointer. This is what we're considering for our window. If it's not in the set, it's safe to include. We add it, update the max length if needed, and move the right pointer forward. If it's already in the set, we've hit a duplicate, so we shrink the window from the left, removing one character at a time until the duplicate is gone. Once the scan is complete, the max length we've stored is the longest substring without repeats. This sliding window brings us down to big O of n time, just 50,000 steps max. Space remains big O of min of n and m for the set. In real-world terms, that's just 128 spots for ASCII, efficient and tight. But we're still doing extra work removing characters one by one. Can we leap over that overhead and jump straight to the right start point? To make that jump, we'll use an array to store the last scene index of each character. ASCII gives us a clean 128 size array and constant time access. We'll also initialize a variable to track the max length we've found so far, our running result. Now we scan with 2 pointers. End moves the window forward. Start tracks the earliest valid position without repeats. We loop until we've covered the string. Each time through, we check the character at the end index and prepare to update our tracking logic. To maintain uniqueness, we shift start to just after the character's last occurrence, but only if it's inside the current window. With our window now clean, we check if it's the longest so far, and update max length if needed. Then we record this character's next position, end +1, so next time we know where to jump. After scanning the whole string, the max length we tracked is our final answer, the length of the longest substring without repeats. This version runs in big O of n time, using just O1 space for ASCII. That's 50,000 steps and a tiny array, blazing fast and memory light. It's also the go-to approach for interviews and production systems. We started with brute force, reliable but painfully slow at big O of n cubed. Then came the sliding window, smarter, faster, big O of n. But we pushed it further, using indexed tracking to jump the window and avoid redundant work. That final technique? It's interview gold. Fast, space-efficient, and battle-tested in real systems. So here's your challenge. Where else can this sliding window strategy save you time and space? Keep digging, keep refining, and always duck into better solutions.